Alright, welcome back. You must be exhausted. This lecture turned out to be really long. This was pulling together parts of two previous lectures when I decided to re-record it. For this last little part of the lecture, I just want to walk through kind of some demonstrations and some examples about this business of geostrophic wind and real winds at the surface, just to kind of show you some real maps of real winds and so on. So like here is a demonstration we're going to do of the geostrophic wind. And on this slide right here, these are real winds. I just happen to have this day in July of 2008 on my hard drive. I don't happen to remember why it's such a strange date. And this is a map. You could think of this as a map of pressure at some height above the ground. That's actually not exactly what this is. This is actually a map, if you look in the top left corner, of 700 millibar heights. What that means is this is how high above the ground you need to go to get to the pressure of 700 millibars. Remember, pressure at the surface of the Earth is about 1,000 millibars. And so basically we're just saying how high above the ground you need to go with like a weather balloon or something before you hit 700 millibars. Strictly speaking, these are contours of height, but it turns out that they work exactly the same as isobars. Whereas if like this area of low height over like the Great Lakes or whatever, New York, that's just like an area of low pressure. It's a cyclone, okay? It's just that we use slightly different symbols and notation here. So we have these contours of height that work exactly like isobars. And if we take a look at them and we put some winds on there, okay, these are the actual observed winds that we're putting on there from like weather balloons and pilot reports and so on. Let me see if I can zoom it in a little bit right here, for example, over the Northeast United States. Again, these are not like these are not the geostrophic winds, which are an approximation to what the real winds are doing, based on pressure gradient force and Coriolis force. These are the actual observed winds, and you see that they're doing about what you would think the geostrophic wind would be doing. They're basically parallel to the isobars. I mean, they're not exactly isobars, they're height contours, but it works exactly the same way. See how they're parallel to them? They have lower pressure. Well, that's actually lower height, but it works exactly the same way. They have lower pressure to their left and higher pressure to their right. And the closer together they are, the stronger the winds are, as indicated by a longer vector. This is a really good approximation. I mean, that's exactly what the geostrophic wind would be showing, and in fact, the real winds show it too. The truth of the matter is, once you're more than maybe a kilometer or so above the surface of the Earth, the geostrophic wind approximation is basically identical to the real winds. The winds above the surface, once you no longer have to worry about friction, geostrophic wind is a really good approximation. If I had just given you this map with these contours and said, where's their strongest wind, you would have known to go where the isobars are closest together. And you would have known to draw the wind such that it had lower pressure to its left and higher pressure to its right. You would have drawn winds almost exactly like this. Let's see if we can do another example. Okay, here again, oh man, this one's even older. This is a map from 2001. Like I said, I was just clearing out my hard drive and finding old cases I used in different classes and so on. But again, this is a map. Now, these actually are isobars of pressure. They happen to be the pressure 3,000 meters above above sea level. So you can see the pressure. We have higher pressures of about 700 millibars over Florida, and lower pressures of about 655 millibars over Canada. These pressures seem kind of low, but keep in mind we're 3 kilometers above the ground, and pressure always decreases with respect to height. So again, we have a map here that is telling us something about where there are cyclones and anticyclones, and where we should be able to draw on this map where we think there's stronger winds and where there's weaker winds and so on. And in fact, that's exactly what we can do. We can put the geostrophic winds on this map. Again, there's something that you can compute if you're in like a 500 level meteorology course, but that's tedious and not really helpful to us. We can just think about the forces and so on, and where there should be stronger winds and where there should be weaker winds. Like if I zoom in across the Midwest here with my little magnifying glass, I can see that we get stronger winds where those isobars are closer together. Makes perfectly good sense. The pressure gradient force is stronger. Therefore, the equal but opposite Coriolis force has to be stronger. And how we get that equal but opposite Coriolis force is to make the wind stronger. Makes perfectly good sense. All right? Just to give it as a counterexample here, let's look at the winds at the surface at the same time. You can see that there are isobars drawn on this map, the contours of pressure. And you can see that centered near Chicago in northern Illinois, there's an area of low pressure. This is a big cyclone across the Midwest. You can see it spans from about Nebraska to maybe North Carolina or something like that. Big area of low pressure. And you can see by looking at the arrows on there, which are the winds at the surface, that they are largely spiraling around that cyclone in a cyclonic manner or counterclockwise manner. And they're parallel to the isobars, but especially if we zoom in a little more closely, you can see that they actually do somewhat cross the isobars from higher pressure to lower pressure. They're mostly going counterclockwise around the center of the cyclone in northern Illinois, but they are also crossing them at about, I don't know, maybe a 30 to 35 degree angle, something like that, as they get dragged in, as they converge towards the center of the cyclone at the surface. Remember, cyclones at the surface experience convergence. Cyclones aloft don't. The winds are just parallel to the isobars. Well, that's really cool stuff. Okay. Now I want to come back just one slide here real quick about something we kind of brushed away. I only mention this because the textbook throws a paragraph or two at you about this. But what about the centrifugal force? I mean, if we have winds going around a cyclone or around an anticyclone, shouldn't there be a centrifugal force associated with that? Well, sure. Yeah, absolutely. And earlier we kind of waved it away and said, yeah, well, keep in mind, it's going to take days for the winds to go all the way once around the cyclone. In fact, longer than the cyclone will be around, frankly. How we used this idea of like a merry-go-round on the playground or something like that. You know, if it took days for you to go all the way around the merry-go-round, how much centrifugal force are we really talking about? And that's fair. In fact, if you actually do the calculations the way you would in like a 500-level meteorology course, it turns out that centrifugal force is not as big as like pressure gradient force and Coriolis force, but it's also not as small as things like friction and gravity in terms of how they affect these winds. Kind of in between. So strictly speaking, there is another force balance, like cyclostrophic balance, like hydrostatic balance, like geostrophic balance, called gradient wind balance. I hate that word, gradient wind balance, that takes into account a three-way force balance between the pressure gradient force, the Coriolis force, and centrifugal force. It's totally cool, but not 100-level material, okay? It takes some pretty fancy math and so on to work that all out. So I'm not really sure why the book takes time to tell you that that even exists, because there just isn't time. But what I will tell you, because those are useful vocabulary words, is that once you start taking into account this other force, the centrifugal force, as the wind goes around cyclones and anticyclones, you can get real winds that differ from geostrophic winds. They can either be super geostrophic, as in super as in beyond, so they are faster than geostrophic, or you can get subgeostrophic winds, sub as in below or less than, where they are slower than geostrophic. The winds are still acting like geostrophic winds in that they are parallel to isobars and all that kind of stuff, but they are faster than you would think they would be, or they are slower than you would think they would be. We're going to actually use these words supergeostrophic and subgeostrophic at a later point in the course, and so, well, this is where your book introduces those terms. Winds that are going faster than is just explained by geostrophic balance are supergeostrophic winds. Winds that are going slower than would be explained by geostrophic balance are called subgeostrophic. Just sort of put a paperclip on that page or whatever, because we will need those terms again later in the course. All right. Man, this was a long lecture. When I re-recorded these lectures, I combined two lectures together, and it just made for a really long day. But what did we learn in this very long stretch of lectures? Well, we took the time to actually figure out that there were 5 forces that act on air parcels in the atmosphere. And that forces acting on that air parcel either produces a net acceleration by Newton's second law, or the forces cancel out by being equal and opposite to each other, and there's some kind of force balance. We learned how we draw the vectors of all these different forces to illustrate and know what they mean for, like, on a weather map. Like, for this air parcel, this is in geostrophic balance, which way is the pressure gradient force and which way is the Coriolis force and stuff like that. And we learned about these force balances, like cyclostrophic balance, like geostrophic balance, that approximate what winds are actually doing. And in fact, in some cases, they're really, really good approximations. Like in the case of cyclones and anticyclones aloft, real winds and geostrophic winds are basically, I mean, they're within like 0.1% of each other in terms of wind speed and wind direction and so on. They're very, very good approximations to what the real wind is doing. And we can figure them out just by looking at a map of pressure. Pretty cool. Alright, before we all collapse in a pile because we're just so tired from these long lectures, let's answer a couple quick questions. Question 16. For a cyclone at the surface, winds rotate blank around the center of the cyclone in the northern hemisphere. Is that clockwise or counterclockwise? Oh, that shouldn't be too big of a deal, but let's make sure we review it, make a choice from those two options, and get a little feedback before you move on to question 17.